about variation principles for discrete integrable systems. And Frank will be the first speaker. You can see the title, but I think you should probably read variation principles for discrete integrable systems.
I allowed myself a little bit some naughtiness in this respect, because I think it should be on. Hello? Yeah. No integrable systems, I would say, because I think discrete and continuous are two sides of the same story. I won't thank the organizers of this meeting, but I will thank the Isaac Newton Institute for giving the opportunity to have this workshop, but also to have had the program in 2009 where this work was really kind of initiated, and I think the program was kind of crucial in that respect. In the meantime, this has grown into a kind of a business, and there are several people who got involved in this work. So my collaborators in this are mostly these three people, although James also has contributed to this work. But there's also work from other people in particular Yuri Suris and his group in Berlin. So this is really about how to formulate variational principles and what are the consequences of that in terms of thinking and ideas for integrable systems. And I think actually that we can maybe be a bit ambitious here, and also kind of think that integrable systems might inform maybe a kind of wider trend in science. So let's go first to the origins, which is of course the classical conventional variational principle. This has a long-standing history. It is one of the foundational concepts of physics, and it expresses this fundamental idea that nature tends to follow the path of least work. We all know that, and this viva that was actually introduced, I think, in the work by Maupertuis and in the 17th century, but it goes back to all the principles in ancient Greece connected to optics and various geometric ideas. In the modern age, it was formulated, I think, first by Maupertuis and Euler, but also there's kind of indication that Leibniz already 30 years or 40 years earlier had similar ideas in correspondences. Of course, we all know from our student years that this is incorporated in the unifying formalisms of Lagrangian and Hamilton, and so it's really very fundamental. And in modern 20th century physics, it appears in quantum mechanics through the finite path integral. So at the end, I will try, if I reach that point, to say something about quantum mechanics. And as such, it is kind of central to what happens in modern physics, in particular in quantum field theory, even in string theory. So this variational principle, deep down, is very fundamental. So I think we're dealing with a rather ambitious project, to be honest. And I want to dedicate this talk to this anonymous referee in the early 1990s, without whom I probably wouldn't stand in this on this podium today. But I do think that actually that the talk, so I will talk mostly about ideas. Sarah will talk more about kind of specific aspects related to discrete systems. But I do want to bring across that maybe integrable systems can inform some new ways of thinking in fundamental aspects of physics. And I think in that respect we should be maybe kind of ambitious. Okay, so the original problem goes back to the question which is related to this idea of multidimensional consistency. We know from all the indications of integrable systems, one of the hallmarks of integrability is the fact that you have coexistence of many equations, or potential coexistence of many equations, both discrete and continuous, and that's kind of generally the property that we call multidimensional consistency, and it manifests itself, for instance, in the continuous world by the existence of commuting flows, higher symmetries, hierarchies, etc., and in the discrete world by existence of backroom transforms, higher continuous symmetries, and this notion of consistency around the cube. So we can think of this as a set of equations, or the coexistence of in principle, maybe an arbitrary number of equations for one and the same function, which may depend on discrete variables, continuous variables, and where we can impose these equations simultaneously. And this is kind of a deep combinatorial fact for those equations, and mostly these equations are nonlinear. So it is the compatibility of that equation that makes, in some sense, the integrability manifest. So, on the other hand, we know also from a long time ago that many integrable systems, both continuous and even discrete, can be written in a Lagrange form, also Hamiltonian form, but in particular in a Lagrange form. And there one would really want to kind of, if the Lagrange formalism is deemed to be very fundamental, then how can we capture this multidimensional consistency in a Lagrange formalism? That is kind of the main question, because if you have a Lagrangian, a conventional Lagrangian, you write down the Euler-Lagrange equation, you have one equation. Of course, you can change your Lagrangian, you get another Euler-Lagrange equation, but somehow that doesn't tell you how these two are related, or if there is any relation at all. So how can we express that in terms of a Lagrange formalism? And that's basically what I said here. So how can we have a Lagrange formalism which kind of describes many equations at the same time on the same one and the same dependent variable? And I think we kind of found the answer to that question. And our first paper was this, which we wrote, I think, during this program in 2009. And the answer I will give in the next slide. But since then, there has been quite a follow-up of papers. So we have shown that this structure not only holds for the systems that we kind of treated as examples here. These were basically lattice equations from the ABS list, but also in other cases, namely for Gelfand Dickey equations of higher rank, and also for multidimensional equations. Actually, this is the only example for so far of a variational principle for a KP type equation, but there this also works. There have been also quite rapid contributions from the Berlin group, and you can actually show that they showed that what we demonstrated here on examples works for the entire ABS list, and we reformulated that in terms of kind of universal Lagrangian structure, which I will mention later on. And then, in order to understand really the basic principles, we went down to so here we are dealing with Lagrangian two forms. We went down to a simpler case, namely that of ordinary differential and difference equations. So then we are dealing with Lagrange one forms. And this is what Sikarin talked about in his talk on Monday. And this we used really as an example to learn how this principle should work. So this was key to our understanding, to go through these examples and actually also show that everything holds on solutions. There has been some recent contributions also, fundamental contributions by Yuri Souris and his group, and in this respect, but I presume that Yuri will talk about that later. Okay, so what is the answer? The answers actually should become extended objects, namely forms, and not only volume forms, which is kind of conventional in Lagrange theory to think of a Lagrangian as a volume form where you integrate over all the dimensionality that you have in your system, but actually forms of arbitrary how do you call it, dimension. And then there is a kind of special property, and that is really where the integrability resides, namely in a so-called closure relation, that these Lagrange forms are closed forms, but not trivially closed. They are only closed on the solutions of the equation of motion, and that makes it non-trivial. So that is that. So these are forms in principle, a multidimensional space of independent variables, and as such, it seems to us that actually the geometry in the space of these independent variables becomes also a factor. In conventional integrable system theory, the space of independent variables is a rather boring space. It's basically the space of flows, but in this theory, this space becomes more more exciting because there is interesting geometry that one should take into account there. Okay, so this I already said. And so there were many examples that we worked through over since our first paper in case of 2 forms, 3 forms, and 1 forms. And it seems from this that actually this is a universal property. It really holds on basically all the kind of key integrable systems that we have examined. And this is what Sikarin talked about, so I won't talk about that here. Yuri, in end of last year, put forward a connection with the Hamiltonian structure, which of course is a natural question. And so he examined also other examples like Toda-type systems. In my talk in at the Sophus Lee Center a few weeks ago, I gave the set of constitutive equations for the higher dimensional lattice equation, and there's also corresponding work that appeared last week in this preprint by Boll and collaborators. Okay, so I think that between Yuri and myself there's a slightly different point of view on this matter, and Yuri will probably expose what his thinking is about this Lagrangian multiform structure. He will probably try and convince us that we should give a different name to the subject, and to a large extent I agree with that point of view, but he connects it to a kind of area, a rather exotic area in mathematics, and I don't really think that we should, in integrable systems, should place ourselves in an exotic area of mathematics where so far nobody has shown any interest in. We rather than sitting on a kind of side branch of the big tree of science, we should really sit in on the main trunk. So I have a bit of reservations how we should actually kind of brand ourselves. So from my point of view, if anything, this should be about physics. And I want to be a bit provocative and give a few citations from Arnold. You might or might not agree with this. Mathematics is part of physics, and physics is an experimental science, and mathematics is just the part where the experiments are cheap. And he has quite a scathing kind of verdict on the abstrahization of mathematics, and so you can read this, especially how it affects teaching, and also how it affects the kind of we tend to think more and more that the science only becomes kind of perfect when it becomes more and more mathematical, and that is maybe a trend that has developed that we should maybe a little bit resist, because we shouldn't be intimidated somehow by the beauty of mathematics and then kind of keep ourselves from doing interesting things in physics. That's maybe the main message. We have to show some courage. Okay, so now a little bit more in concrete things. Here's the notation that I want to use for a few of the formulas, and Sarah will also use a similar notation. I don't want to go over this in detail because you've already seen this. The only thing is that I denote translation operators by this t's. So u is the dependent variable. It depends on all kinds of independent discrete variables, and the shifts in those variables are given by these translations. And here's the precise notation, and p's denote for me parameters. So this is the regular cube for consistency around the cube. I won't go over this because we have seen this many times over. So just to repeat what we want to do, this multidimensional consistency is the fact that we can impose simultaneous set of equations, and in particular discrete equations, on the same dependent variable in any and this would be two-dimensional equations in this first setting, so they involve pairs of independent variables, but then it's embedded in a multidimensional lattice. And the aim is to give a description of multidimensional consistent integrable systems in a Lagrange form. And I mentioned this already, that the conventional point of view doesn't give us that because it only provides us with one single equation. So we need a new approach. And that approach is that, the approach is that the Lagrangians will become extended objects, and that's what we call a multiform. And it resides really on this property which we call the closure relation. So this is that if you choose the Lagrangian in a very well-chosen way, and we work mostly with 3-point Lagrangians in this two-dimensional setting, then in each two pairs of dimensions you have a Lagrangian, and they also characterized by their parameters. And then there is this closeness of these Lagrangians. So this you can actually computationally verify in the examples where that we have at our disposal. So for instance, equations in the ABS list. Here the delta denotes the difference operator, so the shift minus the identity. Okay, so I will say a few words about linear Lagrangians, but in the paper with Pavlos and Sarah, we actually put forward a kind of universal Lagrangian structure which holds for quadrilateral equations, so where we have a quadrilateral equation of this type. The indices here down denote the shifts, just for convenience. These are the conditions that we impose on these quadrilaterals, and then it's very important to introduce these biquadratics, which also were a key element in James's talk on Monday. And so we have biquadratics along the sides of the along the edges of the quadrilateral and along the diagonal, which is this one. And then you can write down a Lagrangian in very general form, but which has this funny structure, namely of double integrals. And I think this is very significant, these double integrals. These are double integrals over where these biquadratics appear in the denominators. And this somehow describes the whole ABS list. This is a Lagrange structure for the ABS list, where you can also even think of this as interpolating Lagrangians, because the kind of lower bounds here you can also take variations with respect to the lower bound variables, and you get also the corresponding quadrilateral equations in terms of this U0. These are conditions on these limits here. So an example would be the Q4 equation, which can be written in this form, P denoting the parameters, and they're in Adler's equation, they are written in terms of parameterized in terms of elliptic function, and this is the corresponding biquadratic. And if you then evaluate this double integral, so one of these kind of terms that appear in the Lagrangian, you get what is basically an elliptic variant of the dilogarithm function. We know very little properties of such kind of integrals or such elliptic dilogarithms, and that would really be needed in order to understand better how this variational principle, how these identities work that are underlying the this closure relation. What is important is that we are talking always about only Lagrangians that hold for this for integrable systems, but from a different point of view, we can think of these as admissible Lagrangians, and in the derivation of this universal Lagrange structure, the admissible Lagrangians is basically uniquely determined under the conditions that we set. So it's a derivation. You get a system of PDEs to solve linear PDEs for the Lagrangian, and you solve it by the method of characteristics. So it's kind of unique, and that is also kind of a new thing, that you actually solve you get a system of equations which you solve for the Lagrangians. Okay. Now, another aspect that that's why I want to wrote down integrable and not discrete integrable, is that continuous and discrete are really two phases of one and the same thing. There's a very close interplay between these two. So on the one hand, we have lattice parameters. These are the P's, here denoted by P and Q. And then we have the lattice variables, the analogs of discrete space and time. And they kind of are in some kind of duality to each other. And so we can always write in all these cases a kind of chain of equations which are interconnected, namely the lattice equations, the partial difference equations, semi-continuous or semi-discrete, depends how you want to view it, equations, which are differential difference, and fully continuous equations. And they're really two sides of the same medal, if you want. So you can impose then on one and the same variable dependent variable as a function of the discrete variables or of the continuous variables, which are the parameters. and then you have all these kind of consistency conditions that hold on solutions. And so I will give an example, and actually I think it's kind of funny to treat the linear case, which might seem to you quite trivial, but even the linear case is not that trivial. Sarah will talk more about the nonlinear case. So the linear case looks like this. Here we have a fully discrete Lagrangian. This is basically you could say the linear version of some of the equations in the ABS list. And there is this quadrilateral lattice equation. So this Lagrangian gives you, the Euler-Lagrange equations gives you an equation which is a weak form of these quadrilateral lattice equation. This Lagrangian will obey the closure relations on solutions of this quadrilateral lattice equation, which you can verify by direct computation. So you write down this expression here on the left-hand side, you use these relations, and then you will find that it adds up to 0. The intermediate step is given by these differential difference equations. So these are like, in some people might like to think of this as master symmetries of the discrete equation, and they have themselves a Lagrangian and semi-discrete Lagrangian, which in fact you can obtain in some sense by a continuum limit from this special continuum limit from the fully discrete case. And one kind of still somewhat open question is there this semi-discrete analog of the closure relation? And there are relations that you can write down, but they are actually related to Nijhoff's theorems, but I won't go into that here. And then there is the further step, namely the fully continuous equations, and those look like this. So these are partial differential equations in terms of the lattice parameters. So the role that the lattice parameters play in the lattice equation, now they become the actual independent variables. And we have a Lagrangian for that as well. And you see, even for the linear case, it doesn't look that trivial. And again, you can show that this continuous Lagrangian obeys the closure relation. But since we are dealing here with a higher order equation, you cannot verify it immediately. You actually need some additional kind of condition on that, which actually is verified on solutions. I'll come back to that in a moment. Okay, so this I want to just flash up because Sarah will go into this in much more detail. So this is how we can think of how this would work, that you actually have an action which is a summing up of all the contributions of Lagrangians along a chosen surface, and each contribution has a directional aspect to it, so that's kind of the form aspect, and then they give contributions to the action for any given surface. But this action now becomes a functional also of the surface, and that is kind of I think a very fundamental aspect, that it's not only functional of the dependent variables, but also of the surface itself. And the closure relation is in some sense the fact that we have criticality with respect to variations in the surface. In the continuous case, we would think of more conventional forms, but in terms of the independent variables, which are the p's here, and then we would have this Lagrangian 2 form, and once again we would think of an action which is a function of the field variables, but also on the surface. And it is the variation with respect to the surface that will give us the closure relation. So this means that due to Stokes' theorem, that on solutions of the equation, but only on solutions of the equation of motion, as the action is independent of the surface under given boundary conditions. Actually, there is also in the literature some interesting technology which can be found, for instance, in this book, where you do actually variations with respect to varying areas and varying, where you change the areas of integration. So that can be found in this book. Okay, so one question is how we should actually formulate then this continuous theory. I showed you already one Lagrangian structure which is of higher order, but there are various other ways of rewriting these systems and Lagrangians. For instance, you can also write it as a system where you have the main field W as before, but you have also an additional field. So now it becomes a system of two equations, and you can write down this Lagrangian for a system. But note that this second field Z actually is itself a form, so that gives some additional difficulties. And then there's also this particular form where actually you can have a Lagrangian in terms of the shifts object. So these are the Wi and Wj. So this is again a coupled system of equations which can be obtained from this fundamental system. And it is in terms of these two variables. So there are various different ways, various options to describe this. So also in this holds not only for the linear case, but also for the full ABS list. So here we have then an action which is kind of a universal action for differential difference case, and with Pavlov's Xenotidis we derive this Lagrangian for the fully continuous case. These F are basically the biquadratics, but written in terms of some uniformizing variable, which is the alpha, and this alpha is the uniformizing variable associated with the lattice variables on the system. Okay, so there's a very general description here where this works, and all these Lagrangians will obey the closure relations we've proven in our paper. Okay, so then you come to the question, what should be the variational formulas? And this is a bit tricky, so I've only kind of partial answer at the moment. It's basically a notational question, actually, but it works like this. So we have the action, and then of course you look at the parameterization of the surface, and then you have different choices of Lagrangian according to the forms that I showed you in the linear case. So either you have a higher order for scalar fields, or you have something which involves a form field, or you have these kind of shifted fields. And so we have to develop that for all these cases. Now we worked it out. Well, the main principles here are the following: that there are two variations that are involved, namely variations with respect to the surface and variations of the fields. So the variations with respect to the surface gives you the closure relations, and then with respect to the field you have to take into account two types of contributions along the surface, and tangential contributions and transversal contributions, or orthogonal to the surface, and they give rise to some constraints. So this will give rise to a whole system of equations that actually are equations for the Lagrangians themselves. And a partial answer to this, but this is a weak answer, is when you look at special types of variations of this type. So it enters, here. So variations are given by this eta, and then if it kind of factorizes, but this is of course special variation, so this is only a weak form of Euler-Lagrange equation. This makes it kind of transparent, but this is not the whole answer to the question. So this is only a weak, sufficient, necessary but not sufficient system of Euler-Lagrange equations for the Lagrangian. Now I want to say a few words about possible implications for physics. Now, it seems to me, and I think there are many indications, that what we are dealing with in integrable systems are some kind of topological field theories or reductions thereof. I wrote actually a paper a long time ago in 1986, which was published in the proceedings of Oberwolfach conference, where I made a connection between integrable hierarchies and actions of Lagrangians of Wess-Zumino-Witten Novikov type, and these are natural objects that enter in this kind of topological field theory, and there are also connections with Chern-Simons theory. There is also unexpected physics hidden in the objects that come out natural, because if you look at these PDEs, which we call generating PDEs, in terms of the lattice parameters, then actually, even if you look at the simplest case, namely of lattice potential KdV, you get actually what is effectively the Ernst equations of general relativity. So there is physics, definitely, and if you do that for Boussinesq, you get actually the system of equations which are the Einstein-Maxwell-Weil equations. So there is a reason to believe that actually behind what we are doing is actual physics. And in the jargon of physics, this is something that put me off when I was a student. In field theory, they usually tend to talk about a theory. Now, what they mean by a theory is always a special type of Lagrangian. So what we're dealing here with in that kind of jargon would be a theory of theories. And in that theory of theories, what we're really kind of saying is that integrable systems, they form in that space of theories a critical point, basically. And that is also, in some sense, reminiscent of renormalization group theory and renormalization group flows in critical phenomena, where actually at the critical point, you get long-range order. And so this issues like multidimensional consistency, which is kind of insensitivity for dimensions, could be thought of as a kind of long-range order in this theory of theories. And okay, let me leave it at that. Now I want to say, can I take one more minute? I want to say something about quantum theory, actually, to end up with. And what I think that this suggests, from the proper point of view, where actually I think variations with respect to the independent variables are also necessary, we are really looking at something where the ambition is to go into quantum theory. But it will be actually something which is beyond quantum theory, at least beyond the conventional quantum theory. So there is a famous paper by Paul Dirac, seminal paper, I think, in my respect, from 1933, published here, where he looks at the role of Lagrangian in quantum theory. So he says here the two formulations, and he meant Hamilton and Lagrange, are closely related, but there are reasons to believe that the Lagrangian one is the more fundamental, and I would like to subscribe to that idea, although we know that there are very many problems associated with things like the path integral. But this paper was really a precursor to Feynman's path integral work. Now, if we think of this theory, I would propose this as my form extension of the path integral. So this is a bit kind of maybe bold. I have no proof for this. I would just like to pose this. So this is a path integral where the following things appear. Here we have the conventional path integral would look like this part here. So we have a path integral measure along some given curve. And this action here depends on the curve. And it is a curve in the space of dependent, gamma is a curve, sorry, in the space of independent variables. So this is a miswriting. Gamma is a curve in the space of independent variables, which now themselves become variational variables, actually, in the system. So actually, in the quantum ideology, one should integrate over these variables as well, actually. And in fact, one could maybe go further. So for those who are familiar with path integral notation, this maybe makes sense. This basically means that you have an infinitely dense multiple integral where you go from between certain points. But this, so we have to introduce a path integral measure in the space of dependent variables as well as in the space of independent variable. And the action is like given in Sikarian's talk, namely it will take this form action. So this is my proposal for a quantum theory that is associated with the one-form structure. And this is what I tend to kind of somehow maybe investigate in the coming time. Why? Well, the extension of the path integral generalizes, and I would say also radicalizes, from modern point of view, also in the theory of loop quantum gravity. And in particular, I want to point to this paper by Carlo Rovelli on the structure of background independent quantum theory. The aim is really to get to some theory where there's background independence, and what they do here is actually integrate also over the subdivisions, over the time, over the parameterizations. So you get a parameterized parameter invariant series. Our proposal is further, we get actually a geometry independent theory. That is the aim. We get a geometry independent quantum theory. And what it also suggests is that there is a kind of a level where actually independent and dependent variables, they start living on the same footing, and that means also the parameters are starting to live on the same footing, and that is kind of an underlying theme to what James, for instance, was talking about in his talk. And then, of course, I should point to this work by Bazhanov and Sergeyev, where they found this master solution of the Yang-Baxter equation, and that relates to Q4, but still I would say this is conventional quantum theory, and we should do something more. There seems to be need for a more, one step more in these constructions to get a true model of what we could call quantum geometry, and that's where I would like to stop. Thank you.
I would suggest that we just continue with Sarah's talk, because that's supposed to be a continuation of Frank's talk, and then have questions afterwards.